Hi everyone, this is Ruth and welcome back to my channel. This channel is mainly about my home lab where I build different setups, test networking tools, and experiment with infrastructure projects. My main goal with this lab is to practice cybersecurity skills in a real environment. So over time, I'll be building out different systems, security tools, and monitoring platforms. In today's video, in this lab, I'll demonstrate how to detect, investigate, and validate reconnaissance activity using an Nmap SYN inside a segmented cybersecurity home lab. Reconnaissance is often the first phase of an attack life cycle. Before an attacker attempts exploitation, privilege escalation, or lateral movement, they first need to identify available services and discover potential attack surfaces. To simulate this behavior, I launch an Nmap scan from Kali Linux against a Windows server and then investigate the activity using multiple security monitoring layers. Throughout this investigation, we'll validate the activity across the attack source using Kali Linux, network traffic using Wireshark, intrusion detection using Suricata IDS, and endpoint investigation using Windows Event Viewer. The goal is not only to detect the activity, but also to understand what happened, how it happened, and what evidence remains behind. Before starting, let's quickly review the lab setup. This environment runs in Proxmox using VLAN segmentation. The devices involved are the attacker, which is Kali Linux and has an IP address of 10.0.60.100, the target, which is the Windows server or domain controller that has an IP address of 10.0.70.2, and these are the security monitoring components. Traffic is routed through pfSense where Suricata continuously monitors and analyzes network behavior. Now, let's begin the attack simulation. To simulate reconnaissance, I'll execute the following command. Let's break this down. The -SS option performs a TCP SYN scan, or also known as half-open scan. Unlike a normal TCP connection, this technique does not fully establish the session. The -SV option enables service version detection, allowing Nmap to identify applications running behind discovered ports. Now execute the scan. Wait for the results. The scan successfully completed. From the output, several services were discovered. This tells us the attacker was able to enumerate active services exposed by the Windows server. But enumeration alone is not enough. Next, we validate whether the activity can actually be detected. Let's move on into Wireshark. I already captured traffic during the scan. The first thing I want to inspect is whether the scan generated TCP connection attempts. To isolate the activity, I apply the filter. Immediately, we start seeing a large amount of traffic. If we look at the source and destination addresses, we can see packets coming from 10.0.60.100, which is Kali Linux, and they are targeting 10.0.70.2, which is the Windows server. These packets are TCP SYN packets. This is the first step of the TCP handshake. What this tells us is that the attacker is attempting to initiate connections across many destination ports. Notice how rapidly the ports change. This pattern is not normal user behavior. This is characteristic of reconnaissance activity, but SYN packets alone don't tell us whether ports are open. So let's continue. Now I'll update the filter. We're looking specifically for SYN ACK responses. These packets represent the target responding back. We can now see traffic flowing in the opposite direction from 10.0.70.2 back to 10.0.60.101. This means the server acknowledged the connection attempt. In other words, the scanned port is open. This matches the Nmap results we saw earlier. So far, we've proven the attacker initiated scans and the server responded. But something important is missing. Did the attacker actually complete the connection? Let's verify it. This time, I apply another filter. And here we immediately see TCP reset packets. This is the most important part of the investigation. Let's follow the sequence. First, Kali sends SYN. Second, Windows replies with SYN ACK. Third, instead of completing the handshake, Kali sends reset. the connection is terminated. That means the attacker intentionally avoided completing communication. This confirms that this was not a normal TCP connection. This behavior is consistent with an Nmap SYN scan, also known as a stealth scan, because the attacker gathers information while minimizing interaction. Then, as the server processes incomplete or abandoned sessions, we can also observe RST packets coming from the Windows server. This is the fourth stage visible in the capture. The server acknowledges the incomplete connection state and forcefully closes the remaining session. So, the complete sequence observed in this investigation becomes SYN, SYN-ACK, RST, RST-ACK. At this point, we've confirmed the activity at packet level. Now, let's validate whether our security monitoring detected it. Switching over to pfSense, I'll open Suricata alerts. Immediately, we can see multiple triggered events. Looking at the alert description, we can observe entries indicating possible Nmap activity. The source is 10.0.60.101. The destination is 10.0.70.2. Suricata successfully identified scanning behavior and generated alerts. This is an important layer because packet captures require manual analysis, but IDS can provide near real-time visibility. Now let's move on to the target endpoint. Looking through the events, we see authentication-related logs. Event 4624 for successful logons, Event 4634 for log-off, Event 4672 for special logon events. Interestingly, we don't see an event that explicitly says Nmap detected, and that's completely expected. Reconnaissance scans often leave very little evidence directly on endpoints. This demonstrates why relying only on host logs may not be sufficient. Network telemetry and intrusion detection provide stronger visibility. Now let's correlate everything together. The attacker machine launched an Nmap SYN scan. Wireshark captured TCP SYN packets. The server replied with SYN-ACK. The attacker terminated sessions using RST. Suricata generated alerts. Windows remains operational with limited endpoint evidence. That full chain gives us confidence in our investigation. This lab demonstrates how combining packet analysis, IDS monitoring, and endpoint visibility can improve detection of reconnaissance activity inside an enterprise environment. Thank you for watching. If you found this walkthrough useful, consider liking the video and subscribing for more cybersecurity home lab investigations, blue team walkthroughs, and hands-on detection labs.